at the end of last class, we started going over this new way of doing a policy evaluation. And this is interesting to know about because it allows you to avoid doing full matrix inverses for large systems. Also, this approach to policy evaluation is very much along the lines of how a lot of reinforcement learning agents will be doing policy evaluation. And so it's just worth looking at this, and it's actually really straightforward once you have value iteration under your belt. And so what we said last time was that we're going to give you I'm going to give you a policy and an MDP, and I want you to give me the value function. And we saw you could do a matrix, you could use matrix algebra to solve for that. But here, what we're going to do is we're going to run value iteration on a different MDP. And it turns out that it's going to be pretty straightforward. But this different MDP is going to be based on pi. And it's different only in the sense that we're removing all actions that pi does not take. And the picture that we ended up with last time was if this is our original MDP and pi in S0 picks A0 and in S1 picks A1, this is the MDP that we're going to be running value iteration on. This is M pi. Okay? So is that pretty straightforward? We know what M pi is. So we said this last time, but how many policies does M pi have? Just one, right? There's one action in every state, so there can only be one policy. And so that one policy is also the optimal policy, right? And since value iteration computes the value function for the optimal policy, we know if we run value iteration on this MDP, it's going to converge to the value function of the optimal policy, which is the one and only policy, right? So it's almost a trivial proof that this approach will work. So that's basically all there is to it. You can implement this in different ways. I think we basically just covered this slide. This is just for your reading at home. So now, this is one way of describing the process of iterative policy evaluation. Like you actually create a new MDP and then you run value iteration. But you don't actually have to create this new MDP. We can just adjust the Bellman backup operator so it only considers the actions of pi. And that's really the way that you would implement this. And so let's introduce this thing that we're going to refer to as the restricted Bellman backup operator. So the Bellman backup operator, normally it has a max over all actions, right? So you go through every action, you say, well, what would it do? What value would I get if I take this action and get the future value? The restricted Bellman backup operator is subscript by pi here, and it's only going to consider the action of pi, right? Instead of the max over all actions, it just considers the action of pi. And if you do value iteration with the restricted Bellman backup operator, it's exactly the same as if you do regular value iteration on that MDP that we just talked about, that M pi MDP, right? So it's equivalent. And so you don't actually have to produce this new MDP. You just restrict the Bellman backup operator. All right, and this would be just the way of doing iterative policy evaluation. And we can just use the reasoning that we've used to show that in the limit of k going to infinity, this procedure is going to converge to v pi. All right, so that's kind of nice. Now, instead of needing to get matrix libraries and hook those up to do policy evaluation, you have another way to do it, which is maybe simpler in concept, and it also is really easy to implement if you already have value iteration implemented. All right. So any questions about this? We're going to see that we can create some new algorithms pretty soon in the policy iteration class that use this type of idea. All right. So now we're going to talk about another class of policy optimization algorithms. So we've talked about value iteration, and that basically just really deals with the value function. Right? Value iteration only iterates over the value function, and it converges to the optimal value function. And we said you get the optimal policy by doing a greedy look ahead with respect to that. This algorithm, policy iteration, and the other thing about value iteration is it converges in the limit of infinite running. Now, policy iteration is a different type of algorithm that literally explicitly deals with policies and value functions, and it's actually going to converge in a finite number of iterations, which is an interesting property. So we're going to study that algorithm, and that's actually the basis for a lot of actor-critic style algorithms, you could say, in reinforcement learning. If you don't know that terminology, that's not a problem. So all policy iteration is going to do is it just is going to iterate through two steps. One is it's always going to maintain a current policy, and then it's going to evaluate that policy. Right? We've learned about policy evaluation already. And then it's going to do a policy improvement step. So we're going to have some way of, if you give me the value function for a policy, we're going to have a way of creating a new policy in a really fast way that is better than this original policy. Okay? So if you give me the value function for a policy, I'm going to give you a way of producing a policy that's better than that original policy. And then we have a better policy, we evaluate it, and then we can get yet another better policy. So pretty straightforward idea. And this is what the code would look like. So start off with a random policy, evaluate it. We'll just assume we're doing matrix inverses now and getting the exact value function. And then this is the magic step, right? If I give you a value function for a policy, how do you produce this pi prime that's guaranteed to be better than pi? That's the magic step. But if we can do that, if you believe that we can do this, then we can replace pi with pi prime and just keep iterating, right? Until no improving action is possible at any state. So that's the property we want. Now it's worth asking, so let's just assume that this has that property. So pi prime is guaranteed to be strictly better than pi, which means that it's no worse in any state. Its value function is no worse, and it's strictly better in at least one state. Okay? So we'll assume that we have this, and we'll show how to implement it. But if we assume that, how many times can we go through this loop, do you think? Like, what's one way to bound how many times you can go through the loop? So I heard somebody say number of states. That's not as clear. There's a more obvious bound.
Pi minus v pi minus v pi prime delta from the delta of v pi minus v pi prime.
V pi, yeah, I'm not sure that could bound the number of iterations necessarily. What are we changing every iteration? Pi. Right. Yeah. Okay. So the number of policies, right? So he's saying that the max that this could go through iterations is the number of policies that there are. And why is that? Why is it bounded by the number of policies?
Because once you've enumerated all of them, you by definition have the best.
Right. And we also know that this is strictly improving each time. So you can't improve your policy, and then go back to a previous one because your value function would have got worse. So it strictly improves every time. And so the worst case is if the thing goes through a sequence of all policies that are improving on each other. Right? And you can create such MDPs, but they're very, you can create such things, but they're very pathological in a sense. So so that's the basic way of bounding the number of iterations, but it's not a very good bound, right? Because how many policies can there be? We've talked about this before. Is it polynomial? Is it exponential in something, right? What's it exponential in? The number of actions or the number of states? Number of states, right? Because we have all these states and we have to choose an action for each one. So it's going to be the number of actions to the number of states power, right? And so the number of actions dictates the you know the exponential factor that we're dealing with. All right, so that's not very good, but in practice, this tends to converge much more quickly than the number of policies. And in fact, we'll talk a little bit about like what you can say about the convergence time. But generally, it converges very quickly if you run this. Okay, so I think we have said this. So the magic operation is this improved policy, right? And so this is our question. If I give you v pi, how do you compute pi prime? That's strictly better. And of course, it can only be strictly better if pi is suboptimal somewhere. And so the idea is going to be, if I give you a state, we're going to say, consider all the actions at that state, and then pretend that after you take that action, you're going to get v pi as your result. Then you take the action that looked best, right? So I'm assuming I have a policy, pi, and now I'm at state S, and I'm going to try to figure out a better action. Like, what is a better action? I'm going to consider all the actions and pretend that I'm going to follow pi after that action, and then take the best action, right? So and that best action may be different than what pi would have selected at state S. Right? So that's just doing one step look ahead, right? Very much like a Bellman backup. In fact, it essentially is a Bellman backup, except we're using it for a different purpose. All right, and it just happens that, and we'll see why. It happens that if this value function that you put through the Bellman backup happens to be the value function of a policy, you're guaranteed that action that the Bellman backup selects is an improved action. So that's basically the intuition, and what we're going to. I guess it's good to introduce this more slowly. So to write this down, it's useful to introduce the idea of a Q function, which, if you're familiar with reinforcement learning, you've seen this idea of a Q function. It's a very, very common thing to see, and the Q function of a policy, okay, is parameterized by a state and an action. It's just the expected discounted cumulative reward, so the expected value, we'll say, of taking the action in state S and then following pi forever after that. Okay, that's what the Q function is of policy pi. And this is the equations, right? It's very much like the value function equation for a policy, except here we say what action is in play. And so the reward function has this action, and then we transition according to that action, but then after that we get v pi as our payoff, right? So it's this immediate reward plus the future reward. This is a standard form that we're used to seeing. And the improved policy is just going to pick the action that looks best, has the best Q value for state S, right? So that's how we're going to define pi prime, the one with the best Q value for the Q function of pi. All right. So is this structure clear? Like the mechanics of what you would need to do, is that clear? Are there any questions about this? Okay. So relatively straightforward, but you get a pretty powerful guarantee with that straightforward idea. All right, so why does this actually work? Right, so we like to know. I mean, that's a pretty pretty important property, right, to know for such a simple operator. And so we're going to go through a proof of why that policy improvement operator actually works. And it's not a difficult proof. We're actually going to go through it in detail here. And so really what we want to do is prove this proposition here, right? So we're in the context where we're assuming that pi prime is the result of policy improvement on pi. And we want to show that pi prime is always at least as good as v pi. And let's remind ourselves, and it's up here, what this means. Like v pi prime, that's a vector, right? Remember when we write down value functions, they're vectors, the size of the state space. When we put a equality or inequality in between two of these vectors, what we mean is that one vector dominates the other. In other words, this one, every state is at least as good or better than v pi. Right? So that's what we mean when we put inequality or equality signs in terms of vectors. All right? And so this is saying basically that pi prime is at least as good in all states, and we're further saying that with strict inequality, if pi is suboptimal. Because we want to guarantee that. Right? Policy iteration wouldn't necessarily work if you couldn't guarantee strict inequality. Because you might hit a suboptimal policy where policy iteration just returns the same policy and satisfies this part of the equation. You need it to strictly improve so that we guarantee we don't loop around policies. All right. So any questions about this statement? Right? Because with this statement, this is really what lets us say policy iteration is going to work and converge with an optimal policy. So you need to understand what this means. So to prove it, we're going to use a few little properties here. We'll just go through them one by one. They're simple once you write them down and think about them. But the first is v pi is equal to the restricted Bellman backup of pi applied to v pi. Right? Now, if you were to write this out, this would be nothing more than the value equation for a policy. Right? So that's all this is saying. This is a fixed point property of the policy value equation. This property here, I think it's still kind of clear, but the Bellman backup, this is the normal Bellman backup that cycles through all the actions and does a max. Right? So what's the best action and then the value that's associated with that. If we consider all actions and we get v pi after taking the action. That's equal to this. And why is this equality true? Anybody have an idea? It's kind of just definitional, but
Because pi dash is obviously acting greedily, and that's what the unrestricted Bellman operator is doing.
yeah, so pi prime was computed by looking at all the actions and picking the one that maximized, well, if I take this action and then I follow pi prime, what do I get? And so this is just storing the max that the Bellman backup would have computed if you did a Bellman backup on v pi. Right? So pi prime is just storing the max at every state over the actions. And so that's why this equality holds, number 2. And then number 3, this is something you can write down. I think I have a homework problem where you'll go through this, but it's a relatively straightforward proof. So this is just the monotonicity property of the Bellman backup or restricted Bellman backup. So if one value function dominates another, then if you do the Bellman backup on each one, you're going to get one. The results are also going to dominate one another. And you can kind of see that, right? The Bellman backup looks at the value function in the next state and it says what if I take this action and then I follow this, I get this value? Um, well, here you're saying, well, what if I follow this action, I get this value versus this value, right, which is no better. Well, it's sort of intuitive that the result of that, you're going to have this same type of inequality, right? If in the future I'm going to get something better than over here than over here, well, this is going to be uh, a better value than this one over here. So any questions about these properties? Because this is these are the only properties you need for the proof. So let's go through and try to do this. So I'm showing you the equation for pi prime here. And we're going to break this into two parts. And there could be simpler proofs, perhaps, but this one seems to be reasonably short. So we're first going to do the non-strict inequality part. Okay, so we're just going to prove greater than or equal to. And then we'll go through with the strict inequality. So what do we know? We're going to write down v pi, and then we're going to say it's equal to this, right? We've already talked about this property here. And that's going to be less than or equal to a Bellman backup applied to v pi. Now, why is that? Why do we have this inequality here? Why do we know this is true?
Is it only backups that a contraction operator towards the optimal?
Sort of, but there's an even more direct way of looking at this. So if we think of this as the restricted Bellman backup operator that only considers the actions of pi, and this is the one that considers all actions, is there a more direct argument?
It's a bigger search.
You consider more options, right? So the Bellman backup does a max over all the actions. This one is only considering one action, but it's also considered in this max. So this is going to be at least as good, right, in all states. So that's why this follows here. And then we've already written down the property of this equality here. The Bellman backup of v pi equals, well, the restricted Bellman backup to v pi prime. All right? But this is the main step of the proof. And what did this show us? It showed us that v pi is less than or equal to v pi prime, the restricted Bellman backup on v pi. Right? So that line of reasoning led us to this conclusion here. Okay? Now, what we can do is we can apply the monotonicity property where we could apply the restricted Bellman backup to both sides and get the same inequality. So we can apply it to this side and then this side, and we get this equation, right, or inequality. And we can continue, and we can keep on doing that. We can keep applying it here and applying it here. And we get a whole series of inequalities. B to the k of pi prime applied to v pi is less than or equal to bk plus 1 pi prime v pi. Right? So you get this for all k, this is going to be true. And that, just chaining those together, that lets you say that v pi is less than or equal to this restricted Bellman, k restricted Bellman backups applied to v pi. Right? So if it's not quite clicking here and you can't quite figure out a question, just go back and study these a little bit. And if it still doesn't make sense, you can ask questions to me or the TA at office hours. But are there any questions on this little line of reasoning here? Yes.
This seems kind of a given for the monotonicity step that if you're applying pi prime, which is the optimal path, then that would just kind of be true by definition. It doesn't seem like you have to really reason it out across k steps.
Yeah, it's not exactly. I mean, the monotonicity property is a true. Once you get past this first step, pi prime is not really the optimal action for any of the other value functions that you're going to be experiencing? It may be, but it may not be. So what we're doing here is we've got a new value function here, right? So when we apply the restricted Bellman backup to v pi, that's a different value function. And it's not clear that that pi prime is going to be the optimal action for that new value function, right? And it probably won't be in a lot of cases, or at least for some k it won't be. So you kind of basically the property that gets you all of these higher order k's is the monotonicity property. You apply this to both sides. So then you get this result right here. So then, what is the limit of this? So applying the restricted Bellman backup k times as k goes to infinity. What does that converge to? Okay. I heard somebody say optimal or restricted Bellman backup. What would it converge to?
Optimal value function
Of what?
of the full MDP.
Okay.
Unrestricted.
So this is only applying pi prime. So it's restricted Bellman backup. So you remember the iterative policy evaluation algorithm that we talked about? That just iterates restricted Bellman backup over and over and over for a certain policy, right? And so that's all this is doing. This is applying the restricted Bellman backup for pi prime k times. And what does that converge to? So yeah, so it's we'll just say the value function for pi prime. Yep. It's the optimal value function for that MDP that only had the actions of pi prime. But that's just kind of trivially the value function for pi prime. So when you iterate this, when you iterate the restricted Bellman backup for a certain policy, it's going to converge to the value function of that policy. And if you go back in the notes, you'll see this is exactly what that iterative policy evaluation algorithm was. Right? So we can say when k goes to infinity, right, we're going to go to v pi prime. And so we've basically shown, since this is true for any value of k, this shows that v pi is less than or equal to v pi prime. Does that make sense? Yeah, these things, the first time you see them, don't feel bad if you're not following. I'm not good at following proofs in class, but it's not. Yeah, there's nothing technically deep here. If you're not understanding it, it could just be you're not looking at the notation right or just missing something simple. So go back. I do expect that you're able to understand this and even be able to reproduce it on a quiz, because this is actually a pretty common proof structure that you'll see with MDPs. All right. So that proves this non-strict inequality, just the inequality part. Now what we're going to do is the strict part, and I think there's probably a simpler way to show this, but this is the way I wrote it down whenever I made this slide. So we'll just go with this. You might find a different way of doing it. So now what we want to do is prove the strict inequality. So we want to prove that if pi is not optimal, that pi prime is strictly better in at least one state. Right? The value function of pi prime is is strictly better in one state at least, and possibly more than one. So that's what this is saying. We want to say if pi is suboptimal, then we want to show this, right? Where the strict inequality here is on vectors again and means that at least one vector position is strictly better here for v pi prime than here for v pi. So that's what we want to show. And we're going to prove the contrapositive. So just for your memory, that seems to be easier here. If you have an if-then statement you're trying to prove, the contrapositive is if not the conclusion, then not the antecedent. Okay, and so this is and proving the contrapositive is the same as proving the original statement. So we're going to prove instead, if not this thing here, then pi is optimal. That's what we want to prove. Okay, so we're going to assume this. So we're going to, since we already know this, right? We've already shown that pi prime is greater than or equal to v pi. We know that this condition of the contrapositive is equivalent to equality. Right? We're saying it's not strictly greater than, and so you have this equality here. And now you can assume the following. So now we can assume this, and then if you, we combine a few things, and we end up with v pi equals this, equals the Bellman backup operator applied to v pi. And after all of that, this is just the Bellman equation. V pi equals the Bellman backup applied to v pi. Remember, the optimal value function is the fixed point of the Bellman backup operator. So since we've shown that this equation is true, we know that v pi must be optimal, right? Because there's only one fixed point. It's the optimal value function. So yeah, there were some gymnastics there, but that's sort of trying to give you a full proof of why the policy improvement operator works. Right? It's one of the most basic operators there is, and it's the basis for a lot of algorithms, including a lot of reinforcement learning algorithms. So it's good to at least see that there is a proof of it working in this exact case where we know the full MDP. All right, so that's basically it. We've proven that policy iteration works effectively. Right, so this is just showing you the policy iteration algorithm again, and we've already talked about how this will converge in a finite number of iterations, which is definitely limited by the number of possible policies. Okay. So any other questions about policy iteration? Right. It's something you could go implement if you needed to. So the convergence, we've talked about the finite number of iterations convergence, and we get the exact policy with the exact optimal policy with the exact value function, right? Value iteration, we had a way of sort of stopping it and guaranteeing that it was within epsilon of optimal. Here we can get the exact thing, and we know it. We have a stopping condition. We know when we've got it. So that's kind of a nice property. So we can talk about the complexity of this. So each iteration, if we think about what's going on here, each iteration, what does it have to do? Well, it's first got to evaluate v pi, right? And if we were to say, what is the computational complexity of evaluating pi, like to get v pi? How would you characterize that? Is it going to be polynomial? Like, how do we get v pi if I give you pi? Do we know one way to do it? We know two ways to do it. What's one way? What's the first way? Solving the equations, right? So one way, and the way that's probably the easiest to think about here, is we can just do the matrix algebra and solve for the value function. And what was the biggest operation in that process of solving the equations?
Matrix inverse?
It's going to be a matrix inverse, right? And that's roughly, it's like a cubic type of, it's cubic in the size, they can do better than that, but slightly better, but roughly cubic in the dimensionality of the matrix, right? So that would be sort of cubic in the number of states in this case. So, it's not it's a little bit scary, but it's polynomial in a number of states. And then here, this operation just goes through each state. Then it has to go through each action. And yeah, to compute this, you actually have to iterate over all net states. But this is going to be, like the square of the number of states type of operation times the number of actions. So the matrix inverse is really what's going to dominate this computation. Although if you're using really good matrix inverse libraries, you very well might have this winning if you're using those libraries, if you're implementing this with some for loop or something. But that's just implementation details. So so it's overall polynomial time per iteration, but we haven't really bounded the number of iterations, right? So we can't say that it's polynomial necessarily. Practically, this will converge after a pretty small number of iterations, and empirically like O of n iterations, but it really seems like O of 1 in a lot of cases. And trying to make an MDP where the policy iteration will run more than n, the number of states iterations, is actually really hard to do. And I sort of know this because when I started my grad career, this is one of the problems my advisor wanted me to work on, sort of showing that policy iteration converges in polynomial time, number of iterations, well, showing whether it does or doesn't. And we were never able to solve that. That was open quite a while. There's been a little recent progress, and you can call this victory or not, but it's sort of where it's just how things worked out. So if you fix the discount factor, what they can show, they can bound the number of iterations, a policy iteration, by this. That's kind of interesting, right? So this would be, it's bounded by a times log of s here, which now this is 1 minus beta. That's nothing to sneeze at, right? Right. That can be enormous, right? So this result has somewhat of a caveat with it, but this is one of the better results that are known now. It kind of makes sense too, right? So for a bigger discount factor, right, closer to 1, you think that the algorithm has to work harder, right? Because you have to think about the future in more detail. And so this is the intuitive result that you would expect. And remember that 1 over 1 minus beta, that's something we called the effective horizon time, right? So this is sort of saying it scales, you could say, by the effective horizon time times log of the expected horizon time, in a sense. And then you have the states and actions in there. And so in general, if you don't treat beta as a constant, it can be exponential, and you can create these weird MDPs where it goes through all policies. This is a fun little exercise, but in practice, that's not what you find, right? So so my advisor had me working on something that, well, I guess we could have come up with this, but we were actually trying to show that this was polynomial time, but it wasn't. So that's one reason we failed, I guess. You can talk about which one is better or faster. There are different trade-offs. Value iteration takes less time per iteration, per full iteration. Policy iteration does more work per iteration because it's doing policy evaluation. I don't really want to get into these trade-offs. They're just different types of algorithms. And I think really the most important thing is to understand these two different types of algorithms and how they work, because they're working for very different reasons. Like one is explicitly trying to improve a policy. Right? That's what it's trying to do. The other is just kind of making little bits of progress on converging towards an optimal value function. So they work in very different ways. They have some similar operations, but But that's really the value of introducing both of these. So, because we're going to see them later on used in reinforcement learning and other types of algorithms. All right, so there is a modification which the annoying thing about policy iteration is you have to do this policy evaluation step, which when you get to giant state spaces you can't even really do that. And so, but for giant state spaces, you might be able to do something like the iterative approach if you have function approximation. We'll see what I mean by that later on. And so we're going to introduce something called modified policy iteration, which is basically just going to do policy iteration, but it's going to do the iterative policy evaluation instead of the matrix exact policy evaluation. All right. And yeah, basically, this is a lot easier to implement to some degree because you don't have to set up the equations, and it's often faster than either one of these, which is interesting. In other words, policy iteration may be doing too much work. Like it's not necessary to fully evaluate the policy exactly to actually get something that you could improve and make some progress. So this algorithm is still guaranteed to converge under some pretty mild conditions. And so here you're just going to, this is finding the new greedy policy. So you start with a value function in this case. And this is just finding the greedy policy. And then we're going to approximately evaluate this policy by doing the iterative policy evaluation for k steps. Right? We're not going to go to k to infinity. K is a parameter of the algorithm here. So it could be 10, could be 100. That's something you could play with. And then you just keep on going around this loop until the thing converges. Right? And it will converge as k goes to infinity. Well, I guess k isn't the right thing here. Is this as the number of iterations here goes to infinity. And you'll see that when k equals 1, this k here, when that's 1, this is just value iteration, right? Because this computes the greedy action that a Bellman backup would have computed for v, and this just does the backup for that greedy action, right? So when k is 1, you just go through this loop once, it's value iteration. When k is infinity, it's policy iteration. Because when k is infinity, you exactly evaluate the policy here in part B, right? And then anything in between, finite values of k is something in between value iteration and policy iteration. All right, so then there's one other thing in your book introduces this, and it's a useful thing just to see because a lot of RL is sort of derived from it. You got this generalized policy iteration where you can kind of do whatever you want. You can mix and match. You can do a little evaluation, a little improvement in whatever order you want to do. So this is just going to do a loop. So you're going to start with both. This maintains both a value function and a policy. So you're going to start with both a value function and a policy. And then you select a state S, right? Just at random, we'll say. So you have to make sure you select all the states. Like infinitely if you were to run this for infinite time. And then you're going to choose one of the following to do. Could be random. You need to make sure that you don't have a situation where you would only do one of those operations. So just choose randomly. Choose to either evaluate, do one step of policy evaluation, right? This is like that one step, or to improve, right, at this state. So find a new policy action for that state. And you just keep on iterating until you are sick of iterating. So this is a very general schema for doing things, and pretty there are some conditions for convergence, which I'm not showing the details of here, but they're pretty mild conditions as well. And this is the type of thing that's really nice because every operation is very simple, right? You're just doing one simple little thing every operation. and there's a lot of flexibility in the order that you do things, like complete flexibility. So it seems like it's also very well attuned to things like distributed implementations, for example. Um, so, so I think that's pretty much all we're going to say about generalized policy iteration. A lot of the RL algorithms that are introduced in your book basically are put in this framework. So any questions about any of this stuff? Because we've pretty much covered the basics of infinite horizon MDPs now. So now what do you know? Well, you know what is an MDP? It's this tuple. You've learned about how do you define the objectives of an MDP, and we had different objectives for stationary, for finite horizon and infinite horizon, and then you learned how to evaluate policies in both infinite horizon and finite horizon, and then how to optimize the policies. We had different ways of doing that. We learned why the optimization algorithms were correct. Right, it's very important, and we saw a little bit about the time and space complexity. And so that's sort of the bread and butter of MDPs, right? MDPs, value functions, policies, and then value iteration and policy iteration. So you want to have those very clear, and I'll be giving you another written homework assignment that will have you dive into some of the details a little more, and you'll get some experience. We'll have you do value iteration. I don't know if we'll have you do another. We may have to move right on to reinforcement learning for your next sort of lab exercise, but we may have time to throw in one little algorithm where we do modified policy iteration or something. We'll have to see how timing works out.